The talk today is titled Interplanetary Transfer Design and Challenges Relevant to Sustainable Human Off-World Community. Well, my name is João Paulo Sanchez. I newly started on the 1st September at Expanse. And the talk is given by myself and Koldo, who can introduce himself. Koldo.
Thank you, Paul. Yeah, so my name is Koldo Zuñiga. I'm currently a part-time student at Cranfield University in the Master degree of Astronautics and Space Engineering. I'm actually a former Cranfield graduate from another MSc in 2009, and I currently work for GE Power as a thermal performance engineer for the last 11 years, where I've been working in different places like Glasgow, London, and more recently in Bilbao, back in my hometown.
Okay, so I guess one of the things I never did within SONet is introducing myself in the sense of my research interest. You know that I do trajectory design, but what exactly is trajectory design is another question. So, so just some of the projects I've been recently involved. I've been involved in a few mission proposals, interplanetary mission proposals for ESA. This is at proposal stage when you submit the proposal. I'm currently also one of these proposals was accepted, which is Comet Interceptor, which is now in phase A or end of phase B1. Yeah, it's in phase B1, and I'm still involved with the trajectory design of Comet Interceptor. So today we will see some of this trajectory design work, which we have been doing together with Koldo. If you want to go to the next slide, Koldo, please. So I will just introduce the background, so the context where they did this thesis, master thesis come from, and then Koldo will present the main part, the technical part of the presentation. Next slide, please. Yeah. So where this presentation comes from, where the work comes from, it comes from the context comes from two different ideas or items. One is basically NUA, this Mars city state that SONet proposed, which made us wonder how the human transportation between Earth and Mars might actually help to develop this city state in Mars. The other comes from the book series from Expanse, from James Corey, which, by the way, James Corey is just a pseudonym. This is two different authors. So this series of science fiction tells the history of humankind that expanded throughout the solar system thanks to a propulsion system that is very efficient. It uses very little propellant and delivers very high thrust. And thanks to this, then humankind expands throughout the solar system. So based in these two things, then we wonder exactly, okay, how the transfers between Earth and Mars and other planets in the solar system might change depend on the different technology, different propulsion systems. Now, we are not rocket engineers, we do trajectory design, but the rocket itself the performance of the rocket can be basically transcribed into a series of figures of merit, which describe what's the actual performance that delivers in terms of accelerating. And this acceleration then allows us to design, knowing what sort of acceleration we can get, we can design different types of transfers. So if you can move to the next slide, please. So typically, the typical Earth to Mars transfer use what is called the minimum delta V transfers. Now, delta V here means the change of velocity, which is equivalent to, say, the change of kinetic energy that you need to have in order to reach a different planet. And Earth to Mars transfer use this minimum delta V transfer simply because the technology we have nowadays is basically it allows us marginally just to reach other planets. So we obviously need to use that minimum energy channels to reach Mars because we don't have any other technology to reach Mars. And that means then that we take about 8 months to reach Mars. And so that the launch windows are relatively infrequent. So every 2.2 years, these launch windows occurs. And that's the reason why you recently had a few spacecraft arriving to Mars last February, because that's one of the launch windows that we have every 2 point something years. And so you have often you have a bunch of missions occurring at the same time. I will also bring up two historic perspectives. One is that even small island states like Iceland and New Zealand have a number of international visitors that is several times larger than its own population. In particular, it's between 3 to 5 times larger than its own population. And so we might consider that, okay, a city-state in Mars of about 1 million might develop, but there will always be a need for a frequent connection, a frequent human transport solution to go from one place to the other. The other I wanted to bring up is that transatlantic crossing, which started for basically passengers in the 1620, took about 70 days, and it was quite a risky business to do. And basically was people were forced to migrate to the Americas because of religion persecution and so on. And obviously this has been evolving to a point in which it was known that there is not much of a risk to cross the Atlantic, and it can take, or it took 3.5 hours with the Concorde. Next slide, please. So just a summary of, or just a brief account of what exactly we need to do to go to another planet. So we need first to launch to a parking orbit, and this will take you about, it will require to gain about 10 kilometers per second of velocity. And this is done with a massive rocket, and just a little tip of that rocket there is actually the spacecraft that you are launching. Once you reach the parking orbit, then you still need to gain further 3 to 4 kilometers per second more of velocity in order to actually be able to escape the gravity well of the Earth. Once you actually gain that velocity and you escape the gravity of the gravity well, then you will still require at least 3 kilometers per second more to actually reach Mars. And from there you can accelerate as much as you want, and this will allow you to get farther and faster. Once you reach the final planet, your destination, you might actually need also to gain some extra velocity in order to basically stay in the planet. So to reach Mars in a minimum energy transfer, you would and you will need at least 6 kilometers per second. That's the very minimum for the best opportunities when the Mars and Earth are in the best position possible. Next slide, please. So just a brief account of what spacecraft are moving around the solar system or has moved around the solar system before. You can see all these in this beautiful picture, all the different spacecraft that has gone to different planets. If we focus on Mars, if you click one more, then you can see that more than 40 missions have actually reached Mars using these minimum delta V transfers. The picture is slightly updated, so there are more than 40 missions now. Go to the next slide, please. So this brings up a typical figure or plot that is used for mission analysts or astrodynamicists to understand when you can actually fly from one planet to the other. So in the x-axis, you have the Earth departure date, and on the y-axis, you have the Mars arrival date. And in here, you can see in the center where you have a point. I cannot point myself because it's not my screen, but so around where you see a 3 and a black dot, you can see the minimum energy transfer possibilities, which are these sort of type 1 short transfers. These transfers, thank you, Koldo. So these transfers occur every 2.2 years, basically. And so if you expand the x-axis to have many of these cycles of 2.2 years, you will see this shape occurring again and again. And this is the reason why these plots are actually called pork chops. You may have heard them in some. You may have heard this before. So pork chops is because these patterns occur and repeats, and at the end they look like different ribs. And someone decided to put that name, and it stuck. So next slide, please. And we will see some of these figures later on as well. So there are three basic concepts of rocketry that I want to bring up before we move into the actual work of Koldo. So these are the delta V budget, the specific impulse, and the dry mass fraction. Next slide, please. So the delta V budget is this term I've been referring to, which is this extra energy, extra kinetic energy that you need to gain in terms of acceleration, total acceleration that you need to gain to reach somewhere. And it's typically used for astrodynamicists to measure the cost of moving from one place to the other. You can see this beautiful picture here that basically maps any different transfers. So from Earth, you can see at the bottom in blue, to different orbits, and then to escape the gravity well of the Earth, and then to reach different planets as well. Next slide, please. Now, the next concept is ISP, the specific impulse of a propulsion system, which is this fraction between the amount of thrust that you deliver with the propulsion system and the amount of mass flow that you need to have in order to deliver that thrust. So the mass flow is the amount of propellant that you are actually expelling through your propulsion system in per second. And this basically depends on the technology that you're using. So typically, a chemical propulsion system so a chemical propulsion system has ISPs that goes from 3,000 meters per second to 5,000 meters per second, more or less. Although typically we refer the ISPs in seconds, which is basically dividing this fraction by the gravity at the sea level, so 9.81 meters per second square. And this is typically done in this way because the test of propulsion systems occur in the ground, and so is typically used in this way. And we will see later on in some other slides that we refer to the ISP in seconds. So current technologies in chemical propulsion system use ISPs of at most 500 seconds. Some current technologies in low thrust use ISPs that have up to a few thousand seconds. And we will talk about this later again with some other technologies that allow you higher ISPs as well. Next slide. Next slide is about the dry mass fraction. So the dry mass fraction is the amount of mass in your spacecraft, the fraction of mass of your spacecraft that is actually not propellant. So it's anything that is you are not going to burn throughout your propulsion system in order to gain velocity. So it includes, if it was a human shuttle, say, from Earth to Mars, it will include all the payload, so the humans, the life support system, etc., the structure of the spacecraft, and so on. And so this also defines the design in one single figure of merit, basically defines the design of your spacecraft. Typical spacecraft, interplanetary spacecraft, have dry masses on the order of 0.4 to 0.5, which means that basically more than half of the actual mass that you launch from Earth is just propellant. If we look at, if we are thinking about sustainable flights between Earth and Mars, they might look at commercial airplanes as well to see what sort of dry mass they have. Typical airplanes have a dry mass of 0.75, and these are obviously reusables, not like spacecrafts. And perhaps the lowest, so an airplane like the Airbus A380, which is one of the largest, has a dry mass of 0.55, so it's larger of a typical spacecraft, although perhaps not much larger. So, and with this, I conclude basically just the introduction of the background of the astrodynamics and basic rocketry that is required to understand what Koldo has done next. And now I'll pass it to Koldo. Thank you.
Thank you, Pau. Okay. So before getting into the results of my thesis, I would like to set a bit the background in terms of the current Mars mission concepts that are being developed nowadays. So that will help us understand where we want to go from there based on the thesis work. So trajectories from Earth to Mars are very well understood and have been used by NASA robotic missions for more than 4 decades. Round trips to Mars and back, however, are more complex, in that the outbound and the inbound legs must be synchronized into an optimum mission plan. The reality is that for the lower energy outbound trajectory, upon arrival to Mars, the Earth is in a relatively unfavorable alignment for energy efficient return. So this unfavorable alignment results in these two very distinct class of round-trip missions to Mars. So the first type is what is called the opposition class mission, and is commonly referred as the short stay mission. And the second one, the one to the right, is the conjunction class mission, which are commonly referred to as long stay. These are very different mission specs, and they have very different characteristics, such as the propulsive requirements, the mission duration, the surface objectives, the human health considerations due to the deep space transit time. So one important characteristic to consider is that the mission repetition rate for identical Earth-Mars alignments, and therefore launch opportunities, is in the order of 26 months. This is what we call the synodic period, is the time that Earth and Mars take to align in equal fashion. So missing an optimum launch window has very different consequences in the opposition class and in the conjunction class. The opposition class mission has a variability of up to 100% in the propulsive requirements, versus a variability of only 35% in the conjunction class. So this makes the launch window for opposition class very, very tight. So this is essentially the two types of missions that you can design to Mars. So now we look at what is being actually designed by NASA nowadays. So NASA has what is called the Design Reference Architecture, which is a memo that they update every certain amount of years, and it represents the latest know-how and planning for sending humans to Mars. Right now, with the goal of a 2037 Mars mission, there will be a combined cargo and crew mission with a couple of propulsive concepts being studied, chemical and nuclear thermal. And we can see from this schematic from the lower right picture that they are choosing a conjunction class mission with 914 days round trip. So being this the first step in sending humans to Mars, this is obviously an exploratory mission, which requires longer implanted stay times to develop the required knowledge and science, to enable future missions. So now, using this context as a starting point, my thesis aims to understand what would entail, from a propulsive and trajectory point of view, to move from where we are now, which is this exploratory concept of mission, to more a commute shuttle bus type of mission, and how long or how far we would be from achieving something like that. So basic questions my thesis aims to answer or to understand is how will propulsion systems evolve within the next 100 years in terms of specific impulse and thrust? What new interplanetary trajectory windows will be enabled by this evolution of propulsion systems? And how this essentially will shape the future of an off-world human society. Just a footnote, only some of these questions have been partially answered up to date, as this is ongoing work. So more to follow in the coming months, which hopefully I'll be able to share with you guys. So before getting into the some of the results I've obtained, I want to run quickly through some important concepts. So firstly, I'd like to briefly explain the analysis methodology that I'm following to calculate the interplanetary trajectories, as this is really the backbone of my work. So some of you may be familiar with the relatively famous Hoffman transfer. If you've seen, for example, the movie The Martian, you might remember that this is the maneuver they use to abort the trip back to Earth and return to Mars to save Matt Damon. But leaving some theatrical licenses aside, Hoffman transfer is a minimum energy maneuver to transfer from one orbit to the other. So this is characterized by a slow transit time, as it is expected from an energy efficient maneuver. And the departure and arrival velocities are always tangential to the departure and arrival orbits, as it can be seen in this graph. Also, the travel arc is always half an ellipse, as the planets are assumed to be 180 degrees apart at the respective departure and arrival times. And this is a huge assumption, as in reality hardly ever happens. As such, the Hofmann transfer is a great example of to teach basic astrodynamics, but has limited value beyond academic purposes. To calculate more realistic trajectories, we need something better, something more stronger. This is the Lambert arc. So the Lambert arc, it's the solution of the Lambert problem, which was defined and solved by the mathematician Johann Lambert back in the 18th century. And it answers the question, how do we travel in space from point P1 to point P2 in a given time of flight? And although the principle of this problem may sound simple, and perhaps solving it on a simplest way is not that complicated, its optimization has extensive ramifications, and it has been subject of endless papers and PhD theses. For the purpose of this work, I'm using a fairly simple algorithm to solve Lambert arc with few optimizations, but without going too heavy on the maths, as really the purpose of my thesis is not to optimize this solver, or to develop a new optimization approach, but to use it to calculate different interplanetary trajectories. And the other concept I would like to introduce is how I have basically related the delta V's of my trajectories to mission specs, to have something more tangible rather than just a given delta V figure. So it's very important for this work to be able to relate the propulsive needs of the different trajectories to what this means in terms of mission specs. So it can be propulsive technology of the engine, a structural design of the spacecraft, or operational concepts of the mission. So in order to benchmark this and to bound this analysis to something manageable, I've defined few options for the mission specs, which in turn will help me and the audience hopefully to understand what level of technological development are we talking about when we say we need, for example, 40 kilometers per hour, 40 kilometers per second. So for this, we start by defining the technology of the engine, which is mainly characterized by the specific impulse. The higher the specific impulse, the more efficient the engine is and more technologically advanced. So here I give some reference values associated to key technologies. Right now we have operational engines that can produce few thousand seconds of a specific impulse, but a very low thrust. It's mainly electric propulsion in some advanced geostationary satellites for communications. But anything near 5,000 seconds and above, and thrusts above 1 Newton plus, or even half Newton plus, we're still a few years away from them. In some cases, decades, I would say. Then we can define the dry mass fraction, the concept that previously Pau explained. So using a reference current commercial airplane, I've selected 0.75 as a reasonable target to have an interplanetary commuter that could ferry passengers on a regular basis. Then this will be really is equivalent to a Boeing 737, this value of dry mass fraction. But also being cognizant that the dry mass fraction can also go a long way in terms of propulsive advantage, giving up some of this dry mass fraction in exchange for higher delta V. I've also considered lower values. So I will also look at 0.65 and 0.55 and how this allows us to reach farther by basically giving up some of this dry mass fraction. And last, I will limit the operational concept of the mission to really whether we refuel on arrival at the planet or if we have to commit to a round trip with a single fuel deposit. So combining all this through the Tsiolkovsky rocket equation, we end up with different levels of delta V that can be associated to different mission concepts. So considering the lowest level of delta V, 14.1 kilometers per second, we see that this is associated to having an engine with an ISP of 5,000 seconds, which could be a fission nuclear thermal or nuclear electric, then having a dry mass fraction of 0.75, and without any refuel on arrival to the planet. As we improve the ISP, of course, the delta V will increase. the same way as we reduce or we give up dry mass fraction and therefore payload, we also gain delta V. And also, of course, if we allow a refueling planet, we obviously improve also the delta V, as we can use one full tank on the outbound trip and one full tank in the inbound trip. So now, going already to the analysis that I performed as part of this work. So the first analysis I've conducted is a one-way trajectory to Mars. I've looked at a full range of departure and arrival dates that will cover a full synodic period, and then selected the most efficient trajectories in terms of delta V. And I have processed this delta V through the rocket equation and plotted to obtain the following results. So looking at this graph, this is telling us first that it's telling us the dry mass fraction that our spacecraft will need in the y-axis for a given engine technology, the specific impulse, and a given time of flight in the x-axis. I've shaded off the part of the graph below 0.75, as I want to remark that really we are aiming for a target of dry mass fraction of 0.75 as an indication of really what will be required to achieve an interplanetary commuter, that would enable to sustain an off-world human settlement with regular trips back and forth. The tables to the right, they are just some selected points from the graph, with the addition of the delta V, which is not shown in the chart. So we can see, for example, for the specific impulse of 5,000, which is the green line, for a dry mass fraction of 0.55, we can see that we get flight times in the order of 35 days, aligned with what is shown in the table. And the required delta V will be 28.5 kilometers per second. The same way, for 0.65, we will be in travel times of 45 seconds, and for 0.75 dry mass fraction, we will be in travel times of 62 days. Few conclusions we can take from this chart. Well, the first one and most obvious one is that really we need engines with specific impulse technologies above 1,000 seconds to really allow us to enable a dry mass fraction high enough for a sustainable interplanetary human transport system. The second conclusion we could take is that 2-month duration trips to Mars are possible with a dry mass fraction of 0.75 using propulsion technologies in the order of 5,000 seconds, such as fission, nuclear thermal, or nuclear electric. More advanced technologies in the order of 10,000 seconds will be needed to bring down this trip time to Mars to 30 days. And the third conclusion I would like to highlight is that the trade-off of dry mass fraction versus trip duration is a very powerful thing to consider. So here really we can see that trading off 10 percent points, 0.75 to 20 percent points, to 0.75 to 0.55, trading off 20 percent points of dry mass fraction will allow us to have the same travel time with an engine of a technology of 5,000 seconds than an engine with 10,000 seconds. So we have to consider that the technological gap from 5,000 to 10,000 can be decades of development, while maybe giving up 20 percent points in dry mass fraction is something we are willing to accept nowadays, not to wait 20 years to develop a hydrogen fusion engine, for example. Here I just mark these two scenarios where both of them you can see they have the same delta V's for different mission specs. I've done the same analysis for Venus and Jupiter, just because they are planets that in the far future can be interesting locations to create human outposts. Venus not in the surface, of course, that will be in the atmosphere of Venus when it's not 400 degrees. in Jupiter, perhaps some of the moons of Jupiter. But without dwelling too much into this, I would just like to comment some conclusions I've extracted from looking at this graph. So for Venus, the optimum trajectories to Venus are faster than to Mars, but in the order of 10 to 20 days faster. The second thing interesting about Venus is that although it's closer to Earth than Mars to Earth, it has a higher energy level at its periapsis. So basically it takes us more energy to brake, to capture Venus. This what means that the minimum possible delta V to Venus is higher than to Mars. So if you want to trade off a lot of a crew cargo mission, for example, where you don't care about the time, you make a very long trip to just have a very cheap and low delta V, the trip to Venus will be more expensive than to Mars in terms of delta V. And this translates more or less in 5% points of loss in dry mass fraction. For Jupiter, well, obviously we require engine technologies way more advanced than to Mars or Venus. We require specific impulses above 5,000 or in the range of 10,000 seconds to allow reasonable dry mass fractions. And even with advanced propulsion technologies, one-way trips will still be 1 year plus. Okay, so now once we understood what it meant doing one-way trajectories to Mars, we decided to look into the two-way scenarios. So now, before going into the results, I will explain what I've done to basically obtain this two-way trajectory or round-trip results. So here we are considering essentially an outbound trip followed by a given period of stay in the planet to refuel, disembark passengers, unload cargo, and embark a new crew, and then followed by an inbound return back to Earth. So first, we start with the outbound pork chop plot. This is basically all the possible trajectories that we have on a given period to go from Earth to Mars, in this case. Then we add an array of possible stay times. In this case, I've considered minimum of 10 days and a maximum of 100 days. And then last, I added the inbound pork chop plot of the return trajectories, Mars back to Earth. And I run an algorithm that combines all possible Earth departures with all possible Mars arrivals, with all possible Mars departures, and all possible Earth arrivals. So a four-fold loop. And then what the result of this is essentially more than 2 million rows of data and partial mental breakdown. So when I recovered myself from this blast of data, I realized that, well, no, I had to do something with this amount of data points. I had to reduce it to something meaningful. And honestly, here is where the fun really began. And looking at different perspectives and find significant trends in this ocean of data points. So the first filtering I've done with all this magnum of data is to segregate data clusters by in-planet stay time. And I only keep the lowest delta V from data points with the same total trip time. So basically all the non-optimum trips that have the same total trip time, so higher delta V's, I discarded. And when I plot this, then we start seeing some trends and some tendencies. So this plot, I will say, is quite telling. To begin with, here we can see how shorter round trips have a higher propulsive requirement, as we could expect. And if we give up delta V, then this comes at a cost of longer travel time. We can also see that the stay time in the planet, which is the different lines here, 10, 30, 50, 70, and 100 days of in-planet stay before going back. This stay time has a clear and non-trivial propulsive cost. So for the same travel time, staying in the planet longer, it really increases significantly the delta V requirements. So this means that when planning round trips, the stay time should be kept to a minimum. We can also see that the derivative of the total mission duration to the stay time is interesting. So an increment of 20 days of stay time, it really costs us around 50 days of mission duration. So this is a 250% sensitivity. Now, to get an idea of really what these round trips look like, I've plotted some of the outbound and inbound trajectories. So looking at the fastest round trip, that's 100 days. You can see here that the outbound is 60 days. We have a very short in-planet stay, and we come back very, very fast in 30 days. Now we go to the first local minimum, for example, going down in delta V, which is here, around 500 days. Here we see that the outbound and inbound travel times are very similar, in the order of 230 to 250 days. Then we continue, and we go to the tipping point in between the minimums, which is where the outbound and the inbound trips are most unbalanced. So here, essentially, as we travel from here to here, the outbound trip has, the inbound trip, the pink trajectory, has increased and increased. And this is the point where higher is the relation of inbound duration versus outbound duration. We can see that we have an outbound trip to Mars of 110 days and then a return of 500 days. And then we go to the absolute minimum, which is at 800 days, which in month, this is 26. So it's not a surprise to realize that this optimum, most cheap trip in terms of delta V falls when we do an inbound return coinciding with a synodic period. This means that we depart on an optimum alignment. It takes us 220 days to get to Mars, and then we return in a long trajectory of 570 to find ourselves again in another optimum alignment of planets. So now, instead of looking at it in terms of stay time, we can look at mission specs and how these different mission specs relate to the delta V's, as we look in the previous slide. So we can put in these boxes that represent the opportunity windows that different mission specs allow. So we can see that with the specs resulting in the most limited delta V, dry mass fraction of 0.75, ISP of 5,000, and no refuel, we are limited to round trips in excess of 700 days. However, by simply giving up 10% points in dry mass fraction and going down to 0.65, keeping the same engine and without refuel, we can see that this window increases exponentially, allowing us now round trips in the order of 300 days. If instead of reducing the dry mass fraction, we simply introduce the option of refueling in Mars before going back to Earth, this opens an even larger window, allowing us now trips in the order of 200 days. Again, with a dry mass fraction of 0.75 and the same propulsive technology of ISP 5000. Beyond this point, really the incremental benefits start to be smaller. So to bridge the gap down to 100 days, for example, we would need, in any case, propulsive technologies of at least 1,000 seconds. And really, you can get to any better than 100 days with top technologies of 10 seconds, refueling at Mars, and dropping down the dry mass fraction to 0.65. So this was the first data filtering. Now the second data filtering I've done is to segregate data by clusters of delta V instead of by stay time. And this time I only keep the delta V's from data points with the same departure and arrival dates, okay, instead of the total flight time. And this basically was done with the purpose of building charts similar to the pork chop plots, to the one-way pork chop plots that we looked at before. but this time containing round-trip information. So the first chart shows data for the most restrictive delta V, around 14 kilometers per second. And as expected, the opportunity island is quite small. Here we can see that we only have this small opportunity of departures and arrivals. Then as we allow larger delta Vs, so here we were at 14, here we increased the allowance to 42 kilometers per second, then we increase it to 85, up to 117. We see that these opportunity islands get larger and larger. No? It's almost like, looks like a stain permeating through a paper, no? That gets bigger and bigger. It should be noted that in each title, I'm putting what type of mission spec this would be, as we always try to associate a delta V value to what this means in terms of mission specs. These charts, however, by themselves, I felt they were not telling us too much. No? So we decided to look into how many round trips we can actually fit within this data range, assuming 10 days between arrival back to Earth and departing again towards Mars. No? So 10 days we can assume to be enough to vacuum clean the spacecraft, refuel, and restock back all the peanuts, no? in the spaceship. So this is what we see as the red dots in these charts. So each of these red dots is a round trip, defining the departure from Earth and the return back to Earth. So the graph with the most restrictive delta V can obviously only fit one round trip. We can see here that we will depart around March 2035, and will take us 2 years and a half almost to be back on Earth in July or August of 2037. Then, as the delta V increases, the opportunity islands grow, which allow us to fit more return trips back and forth. The last graph being the least restrictive in terms of delta V, so 117 kilometers per second, can fit up to 8 round trips. Of course, this is a huge number, and it will be only possible with very advanced propulsion technologies and possibly lower dry mass fraction, no? In the order of 0.55. But perhaps, depending on the purpose of the trip or the colony requirements, this will just make the trick. So the last chart that I wanted to share with you is kind of distillated from the previous charts, and is based on the round trips that we defined in the previous slide, the red dots. I wanted to see if there was some sort of trend or limit in the amount of trips that we could fit per year based on the allowable delta V. So essentially normalizing the average amount of trips on a yearly basis and plotting versus delta V, we obtain the following relation. And I find this very interesting because we can see that there is actually an upper limit on how many round trips to Mars we can achieve in the future, regardless of how much delta V we throw into the mix. I add also this reference table, as we've seen before, because I think it's good to be able to benchmark or to relate when we talk about a given delta V. Again, what are we talking about in terms of mission specs? So we can see that we can start with one trip per 2 years, so a 0.5 ratio, at a reasonable delta V. And we can fairly and easily reach one trip per year. However, beyond this, the delta V's requirements grow rapidly, and it ends up stabilizing at around 1.8 round trips per year. Any delta V beyond this, I think, is more in the realm of science fiction, so I don't think it's really worth considering, except unless we would revise this in 50, 60, 70, or 100 years. So to wrap up, some thoughts. The short-term propulsive technologies, such can be fission, nuclear thermal, or nuclear electric. These are the ones with ISPs of around 5,000 seconds, will likely be ready for operational missions I would say within a decade, perhaps 2 decades. They're already, the science is well defined and there are prototypes being developed. Still, the gap from prototype to operational can be very lengthy and depends on many things such as industry dynamics and politics and so on. So there's a lot of uncertainty. These technologies will enable trips to Mars with durations in the range of 60 days, one way. Now, with in situ fuel production, producing methane from water and CO2, can reduce the trip times from 700 down to 300 days. So this is a key technology to develop, and that can potentially be ready way before we can fly in hydrogen fusion nuclear engines. More advanced propulsion technologies such as fusion, nuclear thermal, ISPs of 10,000 can bring one-way trip durations down to just 1 month and round trips down to 100 days. One interesting trade-off to keep in mind is the dry mass fraction versus travel time. So we know that giving up small amounts of dry mass fraction can allow us to have very short travel times while still not having very advanced technology levels regarding the engine. Some future work that will be developed in the coming months as part of this thesis will be to essentially take these trajectories, which have been all defined on an impulsive basis, and to model them on a low thrust approach, which is a more realistic thing on how spacecrafts are propelled. This will also allow us to understand acceleration times, and this kind of can trickle down to understanding the power plant, specific weight requirements in these nuclear engines. So, well, this is all what I had. Thank you very much.